When we mentioned that there were thousands of names for the same thing in calculus, the slope of a tangent line, slope at a point, instantaneous rate of change, instantaneous velocity, we introduced a new term, and that was derivative, specifically derivative at a point, and we also introduced the notation for it. And that's what our third objective is all about, being able to find the derivative of a function at a point using the limit definition. And you're going to see that it's basically the same thing that we've been doing whenever we're finding the slope of a tangent line. The picture here brings to mind some chemical reactions, and chemical reactions, whatever the reaction rate is, can be described like many real-world phenomena with a derivative. Okay, so here then is the definition of the derivative at a point. The derivative of a function at x equals a, written f prime of a, is f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. Doesn't that look familiar? Doesn't this exactly resemble the slope of a tangent line, right? It means the same thing. So when we are calculating the derivative at a particular point, we're finding the slope of the tangent line at that point, which is the same thing as the slope of the function at that particular point. In the next little slide here, it just barely changed. It changed colors and then put a delta x there instead of an h. We might see it like that. As a matter of fact, one of the first ones we'll practice. We'll go ahead and practice with a delta x so it doesn't scare you. It means the same thing as the h value, however much I change my x by. Or, you remember that alternate definition that we had for the slope of a tangent line? We can do the same thing for an alternate definition for the derivative at a particular point. Here we have f prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a, to bring that x really close to a in order to bring the secant slope down to the tangent slope. So on example 10, we want to write the general equation of the line tangent to the graph y equals f of x at the point a comma f of a. And this is a very common thing that we have to do on the calculus exam. We're given some sort of function and we want to find the equation of the tangent line at that particular point. What two pieces of information do you need in order to write the equation of a line? You need a point, which we have, and we need a slope. How am I going to find that slope? I'm going to find it by taking the derivative of that function at point A. So here's what that would look like. So I have my point, and then I also need my slope. My slope is just simply going to be the derivative of f at A. So that's the slope at A. Those are my two pieces of information. This is what I'm going to use. This is what I'm going to use for my m. And I'm going to put them both into this equation. Y minus y1 is equal to m times x minus x1. Point slope form. All right, and what's going to go into the y1 is this f of a. Y minus f of a is equal to our slope, which we just calculated here. It was tough. F prime of a times x minus, and then my x sub 1 is the a coordinate that we're computed the slope at. All right, and you can leave your answer exactly like that. You might have to take this f of a and add it to the other side, in which case it would just look like this. F of a plus f prime of a times x minus a. All right, let me make this look a little prettier back here on PowerPoint, like so. So we got y minus f of a is equal to f prime of a times x minus a. Again, the f prime of a functions as the slope at that particular point, the slope of the tangent line there, or here it is solved for y.